Welcome to this video. This is video number 4 in my series of videos on Whitehead and Russell's Principia Mathematica. In this video, I'm going to go through section 9 from the first edition of Principia Mathematica, and anybody that's been watching the videos up to this point might have noticed that I seem to have jumped from section 5 straight to section 9. And actually this is because in the first edition of Principia Mathematica there are no sections numbered 6, 7 or 8. In the second edition I believe there is a section 8, but in the first edition, which I'm focusing on in these videos, there is no section 6, 7 or 8, so we're straight to section 9. In this section we introduce 2 new primitive ideas. The primitive ideas are the ones that are written on the board here. So this symbol and this symbol, these are propositions. I'm going to say more about the nature of these propositions as we go through the video. But this one, this symbol here, we would roughly say something like phi x always, and this symbol we would say in words as something like phi x sometimes. So I'm just going to spend a little bit of time explaining these symbols, what they mean, how they're to be roughly interpreted. When we say phi x always, or phi x sometimes, we're not speaking in a kind of temporal sense. So when we say phi x always, we don't mean phi x at all times, nor when we say phi x sometimes are we saying phi x at sometimes but not necessarily at others. We're speaking more in relation to the values of the function phi. Okay, so when I make the assertion, which since this is a proposition, I can assert it provided that it's true. When I make this assertion, what effectively I'm doing is asserting all values of the function phi. In other words, I'm asserting all values with such values of x as makes phi x significant. Okay, and we have to understand here that we don't have a completely unrestricted, unlimited range to our variables here. When I say that all values of x which make phi x significant, there are some values of x which make my function significant, and then there are other values which make my function meaningless. So if I put a value into my function that makes it significant, then I get a proposition which I can judge to be either true or false. Whereas if I try to put a value into my function that makes a meaningless expression, then it is just that, it's meaningless. I can judge it as neither true nor false. It's just not a value of my function. So what I do here is I check out all of the values of my function which make it significant and see that they're all true, and therefore I can make this assertion, phi x always. So when we say phi x always, we're speaking more in relation to the values of the function. Similarly, when I make the assertion phi x sometimes, I'm effectively acknowledging that amongst all of the values of my function, the significant values of my function, there is at least one which is true. There might be many values of my function which are true, but there is at least one value of my function which is true. Okay? So they're just basic interpretations of these symbols, and they're not to be taken as definitions. Please don't think that I'm trying to define these symbols, because these are primitive ideas. So within my system, there is nothing prior to these. Okay? From these symbols, these ideas, new things will follow within the system, but there is nothing prior to these. There is nothing within the system to explain these. They require, within my system, no explanation. But they do require explanation in the sense that as humans we can't just deal with purely meaningless symbols. We do require some kind of interpretation to be attached to certain groups of symbols. So the interpretation that I'm giving, the elucidation that I've been given, or the explanation that I've been given, is using words and terms that are outside of the system. They are not part of the system. I've used the English language because it seems most convenient for me to explain these symbols using the English language, but they're not to be taken as some kind of definition. And this is important in a way because when I explained how to interpret this, I said we're effectively saying that there is at least one value of my function which is true? Well, within my system, we don't have a notion yet of number. We have no notion of one, two, singular, plural, many, at least, number in general, or quantity in general. We've got no notion of any of these. Within our system, this doesn't actually prevent us from using these, but it could be a bit of a barrier as a human being to interpret these if I can't use these notions. But in the English language, we already have these notions, one, two, many, etc. at least. So I can use them to at least explain from a perspective without the system how to interpret these. But again, they're not to be taken as definitions. So I've already mentioned that these two symbols are propositions. They represent propositions. And in fact, they're what we call first order propositions. In contrast to the types of propositions that we have seen up to this point in Principia Mathematica, which we'd call elementary propositions. And there's some very important differences between these two types of propositions that we're going to have to explain, we're going to have to go into some detail about, but hopefully will become clearer as we go through the video. It turns out that in order to deal with these first order propositions, once these symbols are introduced, these primitive ideas are introduced, that we need some new axioms that allow us to manipulate these symbols. Okay, we've introduced the ideas, but unfortunately without some more axioms we can't really do anything with them. So we need to go through introduce some new primitive propositions effectively in order to deal with these two new primitive ideas. If hypothetically speaking we had a finite range to x extended over a finite range of possible values that made my function significant, then actually I wouldn't need to take either of these as primitive ideas. I could just see them in that case as a kind of shorthand in a way, because if there were only a finite number of values of phi for which phi x was significant, then I could just take the logical product of that finite number of values, and that would amount to the same thing as this. Okay, this assertion would amount to effectively the logical product of all of the values of my function, the significant values of my function. And on the other hand, this phi x sometimes would be the disjunction of all of the values. But because my ranges here, the range of values of x, is usually going to be infinite as we go through the Principia Mathematica, then because we don't have a notion of logical product as applied to an infinite number of terms, nor a disjunction as applied to an infinite number of terms, then we can't just see these as mere abbreviations or a shorthand notation for these logical products or disjunctions. Any propositions that we form have to be of finite complexity. So we can't have infinitely complex propositions, not in the system that we're working with. Maybe in other logical systems it is possible to have infinite complexity, but we don't allow it here. So these are genuinely new and different primitive ideas. Again, I'm using the words finite and infinite here. We don't have these notions within our system. I'm just using words that exist in the English language, which is something that exists outside of our system, in order to just explain something a bit more about these symbols. But within the system, such an explanation is superfluous. It's not necessary. In fact, it can't exist within the system. This doesn't fully explain why we need to distinguish between elementary propositions and first order propositions. Why the two different names? Why do we need to distinguish two different types of proposition? Hopefully, in the next section, I'm going to give a fuller account of the distinction between the two propositions and why it's necessary to distinguish between the two types. And the video that I plan to make further down the line on the axiom of reducibility should go into even more detail about the intricacies of the different types of propositions and how they relate to each other. So at this stage, I'm just going to go through a little bit of new terminology before I come to an explanation of the distinction between first order and elementary propositions. I can make various different assertions relating to these functions. So if I've got a function phi, then I could make this assertion here, phi x. And in this case, x is called a real variable. Or I can make these two assertions, sorry. In the first assertion, I'm saying phi x always. In the second one, I'm saying phi x sometimes. In both of these cases, I've got what's called an apparent variable. Okay, and the reason for this being called a real variable is because I can genuinely vary x in this case. As I vary x, I will get different propositions. What I'm asserting here is not a genuine assertion, in a sense, because this is not a genuine proposition. It will only be a genuine proposition once I replace x with a suitable constant value. So if I replace x with a constant a, then this would become a genuine proposition, and then this would be a genuine assertion. But this still has meaning, as we've seen from section 1. We can still interpret this. This is ambiguous assertion, or assertion of a propositional function. But here, x genuinely varies. However, in these two, x doesn't vary in the same way. In fact, there is no real meaning to... I couldn't replace x here with a particular value. It wouldn't make any sense in this case. So, whereas this is a function of x, neither of these are functions of x. These are genuine propositions, and therefore these are both genuine assertions. They assert genuine propositions, which can be judged as either true or false. This cannot be judged, strictly speaking, as true or false until a genuine proposition has come out of this. The comparison is something like, if I've got f of x equals x squared, it's similar to the following analogous situation, I guess. If I've got f of x equals x squared, x can vary, can genuinely vary here. So I put different values of x in, I get values of my function out. Okay, so I replace x with 3, I get 9. Replace x with 5, I get 25. Whereas if I had something like the integral between 1 and 2 of f of x dx, well, x is not a genuine variable. I can't replace the x here with 2 or 10 or any other specific number. So whereas this is a genuine function of x, this is not. This is just a number. This is just a constant. I can't remember exactly off the top of my head what the value is going to be. Assuming this f of x is the same as this f of x here. But it will be some specific value, a constant. So in the same way, we can think of these as, in an analogous sense, as kinds of constants, these propositions. They relate to single propositions, whereas this relates to a possible range of propositions. So we now need to just have a short digression to look at some of the consequences of introducing these two new primitive ideas. Recall first of all that a function is determined only once all of its values are determined. A function presupposes its values, in other words. We can't create more values for a function that has already been determined. And since the values of function are determined by the arguments of the function, then if a function presupposes its values, it must also presuppose its arguments. And in this way then, we see quite clearly that a function cannot appear in any guise amongst its own arguments. There's different ways that a function could appear amongst its own arguments, potentially, but we forbid all of them. I'm going to go through some in a second. For if a function did appear amongst its own arguments, that means that it would be somehow presupposing itself, which we forbid. So as a consequence then, we can't have expressions such as phi of phi, nor could we have expressions such as phi of phi x always, or phi of phi x sometimes. So these are just some examples of how a function might potentially appear amongst its own arguments. All of these are forbidden. Just a little word on the notation as well I'm using here. Sometimes I use this symbol, and sometimes I need to use this symbol. So this symbol here is referring to an ambiguous value of my propositional function. This is referring to the function itself. So if I were to compare with something like f of x, if I just want to refer to the function, I might just say f. But in Principia Mathematica, rather than just saying phi, writing phi, we write phi with an x hat after it, presumably to indicate which variables are involved. But this is just merely said phi. So this is the way that it works in Principia Mathematica. This is the notation that's used, and I feel no compulsion really to change that notation. So one of the effects of imposing this restriction on functions, in that there can't be arguments of themselves, is that it really severely restricts the values that I can actually put into a function. Okay, and to such an extent that I get some nice, clear, genuine totalities of values that I can put into a function that are significant in that function. So if I weren't to have this restriction, then I would just effectively have some kind of unbounded, unrestricted, real variable, but no specific totality, no legitimate totality over which it would range. And in this way, I wouldn't be able to form propositions, these first order propositions, such as phi x always or phi x sometimes, because I wouldn't really be able to, even in kind of a theoretical sense, check all of the values, because there would be no legitimate totality there for me to range over. Whereas once I've got these various restrictions in place, then I get these nice, genuine totalities, these ranges of values of x, which are significant in my function. And this allows me to form the first order propositions such as phi x always. So the apparent variable in this phi x always will range over the entirety of our legitimate totality. Okay, the x might represent a function, or it might represent something called an individual, which I'm going to be talking about later on in the video. So if the x ranges over individuals or functions, this gives rise to something called the hierarchy of functions, or the functional hierarchy. So certain values can go into my function. The function itself, however, can't go into itself as a value, but it can go into other functions, higher up the hierarchy, say. And then those functions in turn can go into other functions as arguments higher up the hierarchy. So I can't ever take a function and go down the hierarchy and put it into a function lower down the hierarchy, but I can place it into functions higher up the hierarchy, potentially. So the hierarchy of functions comes about through these apparent variables, and I'm going to be going through this functional hierarchy in much more detail in the video that I do on the axiom of reducibility. Suffice it to say that the first order propositions that we've seen, so phi x always and phi x sometimes, form part of this functional hierarchy. Okay, now we could also allow x to range over totalities of propositions, sufficiently defined totalities of propositions, and this would give rise to a propositional hierarchy. Now, throughout Principia Mathematica, we're really going to be dealing with the functional hierarchy and not the propositional hierarchy. The propositional hierarchy is useful for illustrative purposes, and what I'm going to be doing in a couple of minutes is giving a kind of illustration which uses ideas from the propositional hierarchy, because it's much easier to explain through the propositional hierarchy. but also what we will see in the video that I do on the axiom of reducibility, that the propositional hierarchy can be derived from the functional hierarchy. So everything that we say about the propositional hierarchy applies equally to the functional hierarchy, which is going to be important with what I go through in a second. Let's have a look at some of the what might be called unintended consequences of the introduction of these apparent variables, or this hierarchy of propositions, or even the functional hierarchy. So the example I'm going to give over the next couple of minutes is relating to the propositional hierarchy. I'm going to allow propositions to appear as apparent variables. But if we remember that the propositional hierarchy can be derived from the functional hierarchy, then basically everything that I say over the next few minutes is equally applicable to the propositional hierarchy and the functional hierarchy. It's easier to explain and illustrate using the propositional hierarchy. Okay, so we're going to have a look at the function. P is false. And one of the first things to note is that this symbol here is kind of a dummy symbol. I could replace it with Q, and I could say Q is false, or replace it with R hat, and R hat is false, and they would all mean exactly the same thing. Okay, so any appropriate symbol basically with a hat over it could be replaced, could replace the P hat here. So we're going to stick with the P hat. And from this function, we're going to form the proposition P is false always. Okay, so this proposition involves this function. So as we know, this proposition then cannot be an argument in this function. So P here ranges over propositions, some appropriate range of propositions. But this can't be one of the propositions that could be plugged into here, because then we're going to get a meaningless expression. But yet, because this is a proposition, I might want to, from this, form the new proposition, which looks something like this. So P is false always is false. And there doesn't seem to be any real reason why I shouldn't be able to form this proposition. I can judge a proposition, a legitimate proposition, as true or false. So if I'm making the claim that this proposition is false, the whole proposition may be true or false itself, but I should at least be able to make the claim that this proposition is false. I'm not asserting this necessarily, but then it would seem that there is a function involved here. Q is false. Okay, but as we've seen, I could replace this P hat with any similar appropriate symbol, Q hat. So that would seem then that this function is the same as this function. But it can't be, because I can't put this proposition into this function. So if this function is the same as this, I can't put it into this function, nor can I put it into this function as an argument. So the only thing that could distinguish this function from this function here is this, the word false. And the conclusion that we draw from this is that the word false seems to have a different meaning as applied to this proposition as this word false has when applied to just P here. So in other words, this use of the word false here is a use of the word false in this sense, and this use of the word false is a use of the word false in this sense here. So the upshot of all this then is that false, this word false will have different meanings as applied to different propositions. So notice that this proposition here is of a different type to this proposition here. And I could also do a similar thing with this proposition. I could say P is false always, is false, is false. And then the third use of false there would have a different meaning to this use of the word false, which in turn has a different meaning to this use of the word false. And that proposition would be of a different type to this, which in turn is of a different type to this. So what we're seeing here is that as we move up the hierarchy, along the hierarchy of propositions, that the word false, as applied at each level, has a slightly different meaning. Remember, this is going on within our system. It's not something that happens outside of our system. It's just within our system. So we've got two courses of action really available to us, at least two courses of action. One is to, we can't get rid of this problem, by the way. So one course of action would be to have a different symbol at each stage. So just like I've distinguished this false from this false, we've got a different symbol at each level. But this is going to get really confusing as we go along. But equally confusing, we could try to just use the same symbol at each stage in our hierarchy. So rather than distinguishing this false and this false here, we acknowledge that there will be a difference, but in the way that we present the false here and the false here, we use the same symbol. Okay? And this is actually the course of action that we're going to take. We're going to take the second option, where we use the same symbol at each level and accept that as it's applied to different propositions, it's going to have a different meaning, rather than trying to use a different symbol for each of the different meanings. So in other words, our false could potentially have an infinite number of meanings, depending on which proposition it's being applied to. The same kind of idea relates to use of, let's say, disjunction, negation, logical product, implication, equivalence, truth, and false. All of these symbols are subject to the same problem as this, and it's not too difficult to show this. So this is something that we're going to have to overcome in some way. We've got to accept this as a problem. There's nothing we can do about it. It's one of the consequences of our system. Okay. The fact that we use the same symbols at each level means that we've got something called systematic ambiguity involved with these symbols. So systematic ambiguity means that there is a difference in meaning in the symbol depending on whereabouts in the hierarchy it actually is. This using the same symbol to represent different things is not actually too unusual, at least in mathematics. For example, if we think about addition as applied to real numbers and addition as applied to complex numbers, these are not the same thing. So I couldn't just take a real number and add it to a complex number. Not unless my real numbers are sufficiently integrated into my system of complex numbers, usually by identifying certain real numbers with certain complex numbers, particularly the complex numbers with a zero imaginary part. But I have to understand that a complex number with a zero imaginary part is still a complex number, and I might identify it with a real number, a particular real number, but it's still a different entity. Okay? Or even more obvious might be if I've got addition of real numbers and then addition between members of some abelian group, just an arbitrary abelian group. Well, I can't just, I might use the same symbol between the two, addition here and addition there. I might call it addition in both cases, but I can't just take a real number and just add it to one of the members of my abelian group. Just because I'm using the same symbol to represent addition here and addition here doesn't mean that the additions are entirely compatible. It's contextual. How I interpret the addition here is different, although sufficiently analogous, let's say, to how I'm using addition over here. So the differences in meaning of these symbols as I go up and down the hierarchy, it is there, but we've got to understand that using the same symbol indicates that the meanings are sufficiently analogous at each stage. in the hierarchy to justify using the same symbol. So in particular, what we'll notice then is that these symbols, as applied to elementary propositions, have a different meaning as they are applied to first order propositions. Okay, and what we've got to do is, or what we hope to do actually in section 9, is to show that under certain circumstances, this difference in meaning is not something that we need to worry about. We don't actually know that at this stage. What we know is that we've got a problem. Potentially a very big problem, but what we're going to show is that provided that we don't allow propositions to appear as apparent variables, then we can understand these symbols in any context. So this brings us to one of the main ideas of section 9. One of the main results of section 9 is to effectively show that under certain circumstances, this idea of systematic ambiguity is not something that we need to worry about. It's not something that really affects us in a big way. So what we're going to show is that provided that we don't allow propositions to appear as apparent variables, then this idea of systematic ambiguity takes care of itself. In other words, that these symbols will effectively automatically adapt themselves to the types of propositions that they're being used in relation to. Okay, so at this stage we can't take that for granted. We've shown that this problem exists certainly in the propositional hierarchy, but because the propositional hierarchy is derived from the functional hierarchy, then as far as we're concerned, this is also a problem there as well. But what we're going to show is that this problem will disappear in the functional hierarchy for us, effectively. It is still there. Systematic ambiguity is still there, but it's not going to be a massive problem that we need to worry about too much. We don't know that at this stage, though. We have to do the work to actually get to that point to show that that's the case. And this is, in a way, one of the reasons, I guess, why the functional hierarchy is preferred over the propositional hierarchy, why Whitehead and Russell chose the functional hierarchy to use and not the propositional hierarchy to continue the development of the theory, because this idea of systematic ambiguity kind of fades into almost non-existence in the functional hierarchy. So this is how we're going to proceed in section 9. We are going to take the primitive ideas of negation and disjunction as applied to elementary propositions, and we're going to define the meaning of negation and disjunction as applied to first order propositions in terms of the meaning as applied to elementary propositions. So we accept now that there is this difference in meaning, and because we've already got the primitive ideas, we already understand negation and disjunction as applied to elementary propositions, we're going to try to adapt the meaning in a suitable way. So that's not to say that we can just start using negation and disjunction and applying it to first order propositions and expect all of the results that we've proved from section 2 to section 5, for example, to just work with first order propositions. This is what we really need to work hard at to actually show that all of those results from section 2 to section 5 apply equally to first order propositions with an appropriate interpretation of disjunction and negation applied to them. So the first definitions that we've got here, the first 4, are defining negation as applied to first order propositions. So we've got negation as applied to phi x always, and then negation as applied to phi x sometimes. Notice that the negation here is applied to the whole of the first order proposition. Here the negation is just applied to the elementary proposition, okay, or the elementary propositional function, let's say, because we already understand this as it's applied to this particular object here. Similarly, for this one, we understand negation as applied to this. The next 2 definitions here are really just further abbreviations, really, of these 2 bits of notation that we've got here. So it just gets a bit cumbersome from time to time to have to draw the curly brackets around everything. So we ditch those and we just write this instead. So these definitions don't really add anything new, as far as we can see. They just introduce some slightly more convenient notation. And then we move on to the definition of disjunction as applied to first order propositions. Now here it might seem that we're being a little bit nitpicky, a bit too picky about things, but we're really not, because we can't assume any properties of disjunction as applied to first order propositions. So yes, we know disjunction as applied to elementary propositions is commutative, but we can't necessarily assume that from disjunction as applied to first order propositions. So that's why we've got two separate definitions defining the disjunction when the first order proposition is on the left of the disjunction and when it's on the right of the disjunction. And that's when we've got phi x always. Phi x always on the left, phi x always on the right. Here, the next two definitions are similar in nature to 9.03 and 9.04, except instead of phi x always, we've got phi x sometimes. Again, we can't assume that disjunction as applied to phi x sometimes is going to be commutative. It's actually something that we've got to show. And then the last two will show how if we've got a first order proposition on both sides of the disjunction, how we can deal with that. So we get the definitions that we've got here. But notice that over here, the disjunction is only ever applied to elementary propositions. So we've genuinely defined the meaning of disjunction as applied to all of these possible combinations of first order propositions, defined it in terms of the meaning of disjunction in terms of elementary propositions. From these definitions, we would also be able to define, for example, implication and logical product and equivalence if we needed to. Really, we're only going to need the implication. We're not going to need logical product and equivalence in this section 9. But formally, we would just take the definition of implication that we have for elementary propositions and carry it over in an appropriate way to first order propositions. Of course, we're going to get the systematic ambiguity involved there with the implication. But what we hope to do by the end of this section 9, is show that all of the propositions that we've proved from section 2 to section 5 will work in formally the same way with first order propositions. So if we take something like P or Q, I don't know, implies P. P or Q implies P, which is one of the propositions that we prove for elementary propositions. What we're going to effectively show is that we can replace the P and the Q with first order propositions, and formally we will get a proposition that works in exactly the same way. We don't know that at this stage. That's what we've got to prove. That's what we've got to show by the end of section 9. And if we can show this, then effectively the problem of systematic ambiguity disappears for us. So now we come to our first few primitive propositions from section 9, and let's just have a little bit of a recap of where we've got to at this stage. We've got our first order propositions introduced, so phi x always and phi x sometimes, and we've got the definitions of negation and disjunction as applied to these first order propositions. But effectively we've got on the one hand elementary propositions and on the other hand first order propositions, but no way to link the two. If we prove some stuff with elementary propositions, then it's good for elementary propositions, but there's no way for us to carry any of that theory over to first order propositions. Nor, similarly, if we do something involving first order propositions, can we somehow transfer over to to elementary propositions? They're effectively, as far as we're concerned at this moment in time, two completely separate parts of our theory, but there's no way to link the two unless we bring in some appropriate primitive propositions. Because if we think about the definition that we gave for disjunction, so let's just take one of them, phi x always or P was defined to be phi x or p always. That was our definition. Well, what this is saying is that what we've got here is effectively a first order proposition because it's got the apparent variable there. But none of those definitions that I had on the board before allow me in any way to get rid of the apparent variable and thus go back to an elementary proposition. I'm stuck with effectively first order propositions. But that's where 9.1 and 9.11 really come into play. Because if you notice here, on the left hand side of the implication I've got elementary proposition, on the right hand side I've got first order proposition. Similarly 9.11, on the left hand side elementary proposition, on the right hand side first order proposition. Now these seem quite similar to these. I'm going to say a little bit more about these in a second. There's nothing saying that these are objectively the primitive propositions that we need to take to allow us to transfer from elementary to first order propositions. It's just that these are the ones that have been chosen for whatever reason. I don't know exactly the specific reasons why these were chosen, but presumably it's because they led to the results that we're really wanting to derive in the most efficient way, I guess. Now this first one here, 9.1, is effectively it's a symbolic notion of an existence theorem within our system. So with an existence theorem, if you think about what happens with an existence theorem, to prove that something exists, you show an example of it. Okay, there might be many possibilities, but to prove that something exists, it suffices to give a specific example of something. Okay, and that's what this is saying. If you can give a specific example of something, then you can claim it exists. Seems fairly obvious, but it's something that, although we take it for granted when we do maybe mathematical proof, we just kind of take stuff like that for granted. We don't really think about it too much. We still need a way of expressing it within our system. Without something like that being inserted into our system, effectively it doesn't work like that. The system doesn't work like that. And we can't just assume that because it seems like such an obvious thing that it must work like that in our system. It will only do so if we formulate the system in an appropriate way to do so. The second one looks very similar, but what this is in a way saying is that you don't have to give a specific instance of something to prove its existence. So it could be this instance or it could be this instance. And from either of these, you can assert the existence. Okay, so notice that both of these will still be true, even if phi x is false, then this assertion will still be true. It's just because from a false hypothesis, an implication always holds true. Okay? So I wouldn't be able to, if I've got a false hypothesis, I wouldn't be able to pass to the thesis using my rules of inference, my rules of deduction, but the implication would still hold. It's just I wouldn't be able to pass to the thesis or the consequent. Similarly here, even if this is false, then the implication will still be true. It's just I won't be able to pass to the thesis. I won't be able to assert the existence of something if I can't actually show a particular example of something. Then I can't actually pass to to this, which means that I can't assert its existence, which is kind of what I'd hope, really. Notice also that because the premises here are elementary propositions, I can still apply my rules of inference 1.1 and 1.11, in particular 1.11, I guess. Because all I require from 1.1 and 1.11 is that the premise is an elementary proposition. So anything implied by a true elementary proposition is true. Well, these are implied by elementary propositions, therefore if this is true, this elementary proposition is true, then I can assert the consequence. So it doesn't matter what the nature of the thesis or the consequence is, provided that the thesis is an elementary proposition. However, it may be that in actual fact I have a first order proposition as my hypothesis. Might be that the first order proposition is true and that it implies something. Well, I can't use star 1.1 or 1.11 there. I need a beefed up version effectively of my rules of inference, and that's 9.12. What is implied by a true premise is true. So it doesn't put any restriction on the nature of the true premise. It doesn't say that it has to be an elementary proposition. It could be a first order proposition, it could be anything that can be true in our system, and if it implies something, then that thing that it implies must also be true. So this is an extension effectively of our rules of inference from section 1. 9.13 is also another primitive proposition that allows passage from elementary propositions to first order propositions. So okay, we've got a couple already, but it turns out that they're not going to be sufficient for what we need to do. So 9.13, in any assertion containing a real variable, this real variable may be turned into an apparent variable of which all possible values are asserted to satisfy the function in question. This is a really useful primitive proposition, because it means effectively that if I say something like, if I assert phi x, remember what this means? This means that I'm asserting that the value of phi will be true, the value of phi x will be true irrespective of the manner in which x is chosen. Okay, so I can choose x arbitrarily and the value that I get will be a true proposition. So that can only happen in a certain sense if all of the values are true. So this is not making that assertion. This is not making the assertion that all values of phi x are true. It's making the assertion that however chosen, the value will be true. But for that to happen, I necessarily really need to have that all values are actually true. But that's a separate proposition, but from this I can assert effectively this. I can change the real variable into an apparent variable, and I can make this proposition. So this is an elementary proposition being asserted. This is a first order proposition being asserted. Now this can't be reduced to a purely symbolic form other than something like this, really. So it's only used as effectively a rule of inference. It won't be used in any other way, so it doesn't need to be reduced to a purely symbolic form. Remember that, as I've said in a previous video, rules of inference do not appear in our symbolism, effectively. They are something that exists outside of our reasoning. They just look for certain patterns, certain sequences of assertions appearing, and then it's like they act on that sequence of, that appropriate sequence of assertions and conclude something. Okay, but they themselves, the rule of inference doesn't actually insert itself anywhere into the as a premise. If it does so, then we've got to use another rule of inference to deal with this premise. So we never actually need this as a premise anyway in any of our reasoning. So it doesn't really make any difference that we can't reduce it to a purely symbolic form. Similarly for this one, actually, we don't need to reduce this to a purely symbolic form because it's only ever going to be used as a rule of inference. Okay, but this is a massively important primitive proposition that's going to be used continually throughout what we're going to be moving on to. So now we come to a new primitive idea, which is that of individuals. So primitive idea, individual. X is individual if X is neither a proposition nor a function. Okay, so here, individual is being used as an adjective, but when I'm speaking, sometimes I'll tend to use individual as kind of a noun. I'll say that X is an individual. Doesn't really make too much difference, but Just wanted to point out that individual here is being used more like an adjective. X is individual as opposed to X is an individual, but it's neither here nor there. So individuals are the things that are effectively going to get us out of this propositional hierarchy and into the functional hierarchy and avoid this problem of systematic ambiguity that I was discussing earlier. Individuals are going to effectively be the most basic type that we have, the most basic kind of thing that we have, and they will be constituents in propositions and functions. So we'll have functions of individuals, and they will be that kind of the next level up, and then these functions of individuals can be arguments in functions of individuals, and so on and so forth, up the functional hierarchy. And this is what we're going to be using throughout Principia Mathematica, the functional hierarchy, rather than the propositional hierarchy. And it's this that's going to get us out of this problem of systematic ambiguity. So we don't actually have a way at this moment in time of telling whether there are actually any individuals in our system. So we just know that an individual is neither a proposition nor a function. We don't actually have any confirmation whether there is such a thing within our system. Once we get onto section 24, number 24, there will be a proposition in there which effectively says that the null class is not equal to the universal class. So in other words, nothing is not everything. So if nothing is not everything, there must be something that is nothing. Therefore, there must be at least one individual, because the members of our classes are individuals. We can have classes of classes and classes of classes of classes, etc. But in our basic classes, the members are individuals. So if we've got a class that is not equal to the null class, that means that it must have at least one member, which must be an individual. Therefore, we must have at least one individual. We still don't have a way then, immediately at least, of showing that there are any more than one individuals in our system. That will come further down the line. So what are these individuals? What kind of a thing are they? What kind of an entity? Well, individuals could be something very abstract, like a piece of sense data, for example. So I might perceive the redness of the cover of a book, for example. This would be an individual. Or it might be a person who is stood there in front of me. But the idea is that an individual is something that is immediately present to us. So in this way, then, the existence of an individual is never called into question. Individuals, the existence of individuals cannot be asserted. So I couldn't take an individual and say X exists. It wouldn't make any sense. But I can't deny the existence either. I couldn't say that X does not exist, because this would be equally meaningless. Individuals effectively just are. There's no question as to their existence, which is in contrast to things like descriptive phrases. So in section 14, we're going to, if we've just got individuals, then effectively we can only form propositions and make judgments about propositions about things that are immediately present to us. But that's kind of restrictive. Very often we want to form propositions and make judgments about such propositions about things that are not immediately present to us. We do this kind of thing all the time. So I might want to make a proposition about my friend who lives 100 miles away. So they're 100 miles away in their house. I'm here. We're not near each other. We can't perceive each other. We're not immediately present to each other. But I might want to say my friend who lives 100 miles away has a nice car, for example. Well, if I've only got individuals, then I can't form this proposition. But using descriptive phrases from section 14, which I'm going to be a few videos away yet, then I can form such propositions. But this descriptive phrase is not an individual. And we've got to be very careful when we deal with descriptive phrases, because the descriptive phrase might point towards an individual, what might be an individual at some point. If we actually go and, if I go and visit my friends, then that person would become an individual. But it might also point towards nothing. So the typical example that Russell gives is the present King of France is bald. So the descriptive phrase there is the present King of France. Well, there is no present King of France. So how can I judge whether the present King of France is bald or not? How can I judge this proposition to be true or false? Is it even a proposition? Well, he gives a solution to this, but the upshot is that the present King of France is not an individual. And also, using descriptive phrases, we're able to form propositions about historical figures. For example, Socrates or Queen Elizabeth I, who can never be individuals now. They were at one time for some people, but they're not anymore for anybody else, for anybody that's currently alive. But we can still form propositions and make judgments about these propositions using these descriptive phrases. But descriptive phrases are not individuals. Individuals are things that are immediately present, undeniably present to us at this moment in time. Okay, now we've got a definition. I'm not going to spend too much time on this. This is not something that's really terribly important to us at this stage. It is there, I'm going to mention it, but it's the definition of being of the same type. So this is 9.131. So there's 8 points here. 8 ways to tell whether U and V, two things, are of the same type. So U and V are of the same type if 1, both are individuals, 2, both are elementary functions with arguments of the same type. Bearing in mind that elementary functions will take individuals as arguments. U is a function and V is its negation. 4, U is phi or U is psi, and V is the disjunction of phi and psi, where phi and psi are elementary functions. And on and on and on and on. I'm not going to go through all of them. So we are still a bit sketchy on the idea of type at this stage, but a type can be thought of as the range of significance of some propositional function. And as far as we're concerned, that's sufficient for us at this stage. The idea of type and types in general is something that gradually unfolds as we go along. So I'm going to be doing a video on the axiom of reducibility, in which video I'm going to go through the propositional hierarchy and types and things like that in much more detail there. But even then, there's still more that we need to take into consideration. So types are something that gradually unfold as we go through. So I'm not going to be worried too much about this at this stage. I'm just going to get on with the rest of the theory now. Let's have a look at the last two primitive propositions from section 9 then. So the first one is 9.14. If phi x is significant, then if x is of the same type as A, phi A is significant and vice versa. So what this is saying is that if my function is valid at a particular value, x, and A is of the same type as x, then my function must also be valid at A as well. So the interpretation of this, I guess, would be that my function is valid on the whole of a type. My function can't just be valid on part of a type, it must be the whole type. So it's kind of an all or nothing situation. Either the function is valid on the whole of the type or none of the type. If it's valid on none of the type, then it must be valid on some other type somewhere. But I can't have a function that is just valid on a little bit of some type and a little bit of another type and a little bit of a third type. It's all or nothing. 9.15, if for some A there is a proposition phi A, then there is a function phi and vice versa. So what this is saying is that propositions can't exist independently of propositional functions. A proposition must have come from some function. Okay? And because A is a component in this proposition, then effectively A must be an argument in that function. So in other words, we can't have types, we can't have propositions, nor can we have types that are not the range of significance of some function. So types don't exist independently of functions. And vice versa, we can't have a function that doesn't have a range of significance. Every function must produce some, at least one, significant proposition. And just a reminder, significant doesn't mean true. Okay, so the difference between significant and meaningless, or not significant, is not the same as the distinction between true and false. Significant propositions may be true or false, but meaningless propositions, meaningless expressions, because they're not propositions, are neither true nor false. So all we're saying is that every function must produce some propositions which are capable of being judged as either true or false. So that means that every function gives rise to a type, and every type is the range of significance of some function. The two don't exist independently, so we can't have just propositions just floating around in our system, just completely disconnected from any function. Okay, so they're the final two primitive propositions from section 9. So what we're going to move on to now are some propositions which are fairly straightforward to prove. I'm not going to go through all of them, I'm just going to go through one of them, but I'm going to state the other ones. But these are the ones that actually require some demonstration, and they're kind of preliminary propositions for what we're really wanting to move on to with this section. There's only 5 of them, so I'm going to go through them quite quickly. Let's take a look then at the first few propositions from this section which require demonstrations. So I'm not going to go through all of the demonstrations of this. I've written one of them out, but even then I'm not going to be going through the whole thing line by line. There's just a few points that I want to make on regarding this demonstration. Actually, I miscounted a few moments ago. I said there were 5 such preliminary propositions. There's actually 6 of them. Also, apologies for this looking a little bit drunk. I only realised after I'd written it all out, and I didn't really want to write it all out again, so it's just going to have to stay as it is. So 9.2, proposition 9.2. This is an important proposition, even though it's fairly straightforward to prove. The demonstration's only a couple of lines long. What this allows us to do is to argue from general to particular. And bearing in mind that we've already got propositions, primitive propositions, which allow the passage from elementary propositions to first order propositions, this is going in the other direction. Notice we didn't actually have any primitive propositions which allowed passage from first order to elementary propositions, but that's the first proposition that we end up proving in this section, the passage from a first order proposition to an elementary proposition. And what we're also starting to see now is how some of the principles that we use in mathematical proof, which we kind of take for granted, are starting to be built into this system. We've got to remember that our system is it's being built from nothing, effectively. We can't assume that it's going to behave how we want it to behave. Even if something seems blatantly obvious to us, we can't assume that particular behaviour will be present within our system. We have to make sure that certain behaviours are in our system, so that our system behaves in the way that we want it and expect it to behave, so that it reflects effectively mathematical reasoning as it was at the start of the 20th century. We want our system to mirror that kind of reasoning. So even though mathematics before the 20th century, so the end of the 19th century, didn't really use formal systems, it used reasoning, and it used particular techniques, but these were never formalized. But here now they're starting to be formalized. So we've already seen with primitive proposition 9.1 how if we want to prove the existence, or if we want to assert the existence of something, we have to give a particular instance of it. This seems fairly obvious. If I can give a particular instance of something, then I can assert its existence. It is obvious outside of our system, but within our system we need to make sure that that principle is there, it's accounted for. We can actually do that within our system. And this is kind of going in in a different direction. It's saying something like, if something is true for all of a particular type of object, then it's true for any particular one. Okay, and that's what we're seeing here. So in other words, well, let's say something like Euclidean triangles. The angles in all Euclidean triangles add up to 180 degrees. So that means that if I take a particular Euclidean triangle, I can say the angles in this triangle add up to 180 degrees. Seems like such a blatantly obvious point to make, to the point of triviality and almost absurdity. But we have to remember that that wasn't there in our system necessarily. We can't, as obvious as that principle seems to us, we can't just assume that it's there as part of our system. Okay, moving on to 9.21. I'm going to leave this just for a second. I'm going to come back to the proof. I'll just state the proposition. What we're seeing in this proposition is how the scope of an apparent variable can be manipulated to a certain extent. In fact, we've already seen this with the definitions that I gave right at the start. So definitions 9.04 to 9.08 or whatever they were. Some of those allow us to manipulate the scope of an apparent variable. Now I'm going to talk more about the scope of an apparent variable in the next video, but suffice it to say that the scope of this apparent variable here is the whole of this implication. The scope of this apparent variable is just the phi x, and the scope of this apparent variable is just the psi x. So the scope has effectively been changed, it's been manipulated, and we're going to need to be able to do this at various points throughout our work. 9.22, very similar in appearance to this, but not only do we change the scope of the apparent variable, we actually change it from an always to a sometimes. Okay. 9.23 and 9.24 are similar in nature to proposition 2.08. So if we think what proposition 2.08 was, it was P implies P, where P is an elementary proposition. But here we've got first order propositions. We've got one of each kind. So we've got the phi x always implies phi x always, and phi x sometimes implies phi x sometimes. So there's a very similar appearance, formal similarity between these two propositions and this, which is 2.08. 9.25 is effectively one of our definitions. Remember that definitions are not propositions, so I can't assert a definition. If I want to use a definition as a proposition, I've got to turn it into a proposition that I can actually assert in my reasoning. So it's fairly straightforward. It's an application of 4.02 and the definition, I can't remember, 9.06 or whichever one it is, I can't remember off the top of my head, but it's a very straightforward derivation. So this follows straight from our definitions. Okay, so there's just a couple of points that I want to make now regarding this demonstration. So let's take a look at this demonstration. What I want to look at first of all is the first two lines of the demonstration, because there's something that seems slightly strange about this, in the sense that if we look at what's written on the first line, all of the variables are z. So that would suggest that they're all the same. They're all the same variable. But then on the next line, we suddenly change one of the variables to a y. The fact that it's changed to an apparent variable is justified through this 9.1, use an application of 9.1, our existence theorem, if you will. So how is it possible for us to just change one of the z's to a y, but not the others? Well, I guess the only explanation to this would be that all of these z's here are not actually all the same variable. they're actually, in a way, independent variables. So the explanation that I'm going to give is the following. If I can assert this, which is the top line, the first line of this demonstration, then this is ambiguous assertion. So if I can assert this, then that means that this proposition must be true for at least one value. So let's say it's true for z equals a. Then I can assert phi a implies psi a implies phi a implies psi a. Okay, so this is one particular value. Now, if I I only know that because this has been asserted. If I can't assert this, then that means that it's never true. It's not true for any value at all. Okay, so what I can do then is I can say, well, if phi a implies psi a implies phi a implies psi a, then that means that if I just change that to a y, psi a, then there must be a value of y which makes this true. And there is. Y equals a. Y equals a makes this proposition true. So therefore I can say, there exists a y. There exists a y such that da-da-da-da-da-da. Okay? And that y happens to be when y is equal to a. So that means that I get this assertion, which is the second line here. Now, okay, I changed the z's to a's, but I didn't actually need to do that. So that explains, I hope, the transition from the first line to the second line. And it also explains the transition to the third line as well, because a similar trick is played where these z's are both changed to x. So these z's here can be the same variable if we want them to be, but they can also be different variables if we want them to be. It might be that we choose some of them to be the same and other ones different. It depends how we want to, exactly what we want to do, exactly what we're wanting to prove. And the last thing that I want to just point out is on the last line of this demonstration. So if we look at the last line here, it would appear that I haven't actually proved what I wanted to prove. I needed to prove phi x implies psi x always, implies phi x always implies psi x always. But I don't have that. I've got the phi x implies psi x always, but then I've got phi y always and psi z always. And the reason for this is that the apparent which symbol I use for the apparent variable doesn't make any difference. So for example, if I've got x psi x, this would be exactly the same as y psi y. It would be the same as z psi z, for instance. These all mean exactly the same thing. So in other words, these are as good as, this is as good as this, and this is as good as this. So once I get to this stage, even though it seems that I'm using different symbols in the apparent variable, actually makes no difference. No difference whatsoever. In an apparent variable, I can always just change the symbol and still get exactly the same thing. So I could change this to a t, provided that I change this and this to a t, because these are both in the scope of this apparent variable. I get exactly the same thing. Okay, but if I change that to a t and I don't change these to a t, then I've genuinely changed the meaning of the proposition, or the part of the proposition. So as long as I change the symbol here and any symbols that it corresponds to in the expression, then I get exactly the same expression. It doesn't change anything. So now we come to what really we've been driving at throughout the whole of this section 9. So what follows now is a bunch of propositions. I'm not going to go through all of them. I've written a selection of them up on the board, and I'm not going to go through the demonstrations either because they're fairly straightforward. But what we've done is, what we're doing effectively is considering each of the primitive propositions from section 1 and now proving some kind of analogous proposition that applies to first order propositions in some way. So as an example, I'm just going to copy out of the book. Let's take primitive proposition 1.5, which is P or Q or R implies Q or P or R. Okay, so what we do then, because we've got three elementary propositions, so this is 1.5, star 1.5, primitive proposition. We've got three elementary propositions involved in this expression, in this proposition, P, Q and R. So this is the analog. This is one of the analogues of star 1.5 from section 9. And what we've done is we've left P and Q unchanged, and we've replaced R with a first order proposition, in this case phi x always. And we've proved that we can get an analogous proposition from that. So this proposition here is formally identical to this proposition here. Okay. Once we've done that, then we can do the same thing. We can replace R with not phi x always, but phi x sometimes, and prove another proposition, analogous proposition. And then, okay, we can go on again to leave P and R unchanged and replace Q with phi x always. And then another one, leave P and R unchanged and replace Q with phi x sometimes. Then Q and R unchanged, replace P with phi x always, and then phi x sometimes. And in this way, we're going to get, corresponding to primitive proposition 1.5, we're going to get 6 propositions. I've just written one of them here, but we're going to get 6, a series of 6 modified propositions corresponding to first order propositions, where one of the elementary propositions from 1.5 is replaced with a first order proposition. All of these propositions will be formally identical. And we can do this for all of the primitive propositions from section 1. So this is one of the analogues for 1.2, one of the analogues for 1.3, 1.4, 1.5, 1.6, but there's several of them. There's 2 in this group, there's 4 in this group, I think, and then I think there's 4 here and 6 here and 6 here. 6 analogous propositions. And then we've also got analogues of 9.7, 9.71 and 1.7, 1.71 and 1.72. And that takes us right up to proposition 9.63. So once we get to 9.63, we've effectively proved that if we take each of the propositions from section 1, the primitive propositions, and replace one of those elementary propositions with a first order proposition, we can prove a formally identical proposition to that primitive proposition. So once we've done this, once we've achieved this, then we can say, right, well, for what it's worth, we can go on then to prove all of the propositions that we proved in section 2 to section 5, we can prove similar analogues. For each of those propositions, we can replace one of the elementary propositions with a first order proposition and and do this for in all of the possible combinations and get a series of formally equivalent, formally identical propositions where we've got one first order proposition involved. And then we can go through the whole process again, not just replacing one of the elementary propositions with a first order proposition, but replacing 2 elementary propositions with 2 different first order propositions. So I might replace R with phi x always, and replace Q with psi y sometimes. And there's going to be all sorts of combinations that I can prove here. And then I can go on and show that I can replace 3 of the elementary propositions with 3 different first order propositions. And so on and so forth, as much as I need to do this. So if I happen to prove a proposition involving 26 elementary propositions, then I can go through this process 26 times and get an equivalent proposition, or a series of equivalent propositions, and there's probably going to be a lot of them, corresponding to 26 first order propositions. So in this way, I can take each of the propositions from section 2 to section 5 and be sure really that I can replace any of those elementary propositions with first order propositions, and I get something that works. And the disjunctions and the negations and the logical products and equivalences and implications and everything will all effectively adapt themselves automatically to fit the particular type of proposition that I've got involved in my proposition altogether. So what we can see now is that this problem of systematic ambiguity kind of fades away. Okay, so right at the very start of this section, when I went through systematic ambiguity, it seemed like a genuine problem, something that we were going to have to work around, something difficult that we were going to have to live with. But because we've set things up in the right way, we've gone about things in an appropriate way, we've actually managed to show that the idea of systematic ambiguity can be kind of pushed to one side. We can't forget about it completely. It is something that we've still got to give a little bit of consideration to as we go through here and there, but it's not going to be something that's going to be so much of a thorn in our sides. So now that we've shown that all of the propositions from section 2 to section 5 involving elementary propositions can be generalized to first order propositions, then we can actually continue this process higher and higher up the propositional hierarchy if we wanted to second order propositions, etc. But we don't actually need to do this in practice, because we only ever really need to consider kind of relative orders. We never need to consider absolute orders of propositions. So what are elementary propositions in one context might actually be first order propositions in another context, for instance. So what we can do is we do need the approach of section 9, which allows us to transition from elementary to first order propositions. But once we've done that, what we effectively can do is take our first order propositions and define these as new elementary propositions, and then go through the whole process again, and we get some new first order propositions, which are effectively our old second order propositions. So we do need the approach from section 9 to make that transition, but once we can do that, we can do it for between any two orders, and we can just continue the process as long as we want, although in practice we don't need to. In fact, just to make the transition from elementary to first order propositions is going to be complicated enough, and to do it in its entirety, to accomplish that in its entirety, is going to take some considerable time. It's going to be very time consuming to do that. So we accept that we can do it, but we don't actually write everything out necessarily. Okay, so that brings us to the end of section 9. Section 10 is next, and in section 10 we're going to be changing approach slightly. So what's in section 10 is not a mere continuation of the contents of section 9. So it will become clear in the next video what I mean by that, which approach we're going to be taking. But that's not to say that what we've done in section 9 is irrelevant. It's just that we are going to be changing the approach a little bit. We're going to be looking at an alternative approach to what was presented in section 9 without necessarily discarding the results of section 9. So that brings us to the end of this video. Thank you very much for watching. If you do have any questions about anything that I've gone through in these videos, then please feel free to get in touch with me and leave any comments to the video in the comments section below. Because I understand that there is a lot to go through in these videos, and I don't necessarily get absolutely everything in that I would like to get in. The videos turn out to be long enough as they are. If I were to include even more stuff, they would be even longer. So there are necessarily going to be some gaps in there. But if you pick up on any of the gaps and you want them clarifying, please get in touch with me and I'll answer your questions to the best of my ability. But thank you for watching this video, and I look forward to seeing you in the next video.